Alright, time for another draft physics video presentation. I think that's what I intended to say. Still confused. See this little icon here for the recorder, and it's supposed to do something. It's supposed to indicate that there's a recording taking place, and it doesn't do that anymore. So there's no way to tell whether the damn thing is running. And you can't be sure of the shortcut keys. They're just not reliable enough. And, you don't want to make an hour video when it's not recording. And anyway, so it's a little bit annoying. But there's a lot of things that are annoying. This tablet is crashing. So it's, making obnoxious noises. Anyway, it's just nothing. I have to upgrade my technology one of these days. Anyway, alright, so we'll just do some more of the same, I suppose. So we'll start with some comments and, get depressed. And try to endeavor to persevere. Alright, so it does keep on moving in space. That would be contrary to conservation of energy. It doesn't keep on moving in space. So again, you want to argue facts. Okay, fine. I don't see much point. I'm just saying as a fact, I can't find any information indicating that protons and electrons are capable of moving forever. The idea would be is that they're actually pushed, and the evidence is sort of strong for this. So I could cite a couple of different experiments where it's clear we can't do what we theoretically should be able to do. Now, light's a little complicated. Okay, finding trapping light perpetually is complicated because the mirrors are the problem. It's kind of almost impossible to make a mirror that always interprets light as photons and always reflects them. So they're always getting consumed. Now, a fiber optic cable does fairly well. The light goes pretty far through it, it gets bounced around, and it stays in the container. And so, in a fiber optic cable, we can move light around kind of a long time. But the fact is that it's not forever. Okay, you can't do what theoretically should be possible. Now, so I would say that we can't do it with light for a reason. Now with electrons, the truth is that once you put them in a magnetic field, it's like putting them, as I pointed out, it's like creating gravity for them. So it's like creating another force that keeps them, that turns them. So they don't lose any of their momentum. They don't have to use, like a track runner has to use his own momentum to turn. Or a car on a highway has to steal some of their velocity to turn, some of their momentum. Creating more friction and doing other things to create the turn. Now, if you could do it with wind, blow the cars with a strong wind or some other kind of mechanism, then they could turn for free and go further on a gallon of gas, you could argue. Well, the point is that electrons and protons just don't do this. Once we put them in an accelerator, we can't just keep them going. They just don't appear to have anything like perpetual motion, like wrenches thrown in space. They don't go forever. Now, I guess you could theorize that if I made a magnetic wrench and in space I create a nice orbital round magnetic field for it to run through, that I could throw the wrench in and the wrench would just keep going around and around and around for thousands and thousands of years. So I'm just saying it's getting rid of the friction argument. And when you do that with electrons and protons, they don't appear to have any durability. Okay, even the radioactive elements kind of show this, is that the electrons shoot off and fizzle out. And, they'll come out, and they'll go a certain distance and no further. They get their energy gets absorbed somehow. Now, I would argue the simple explanation is that the electrons and protons are actually being pushed by things like gamma rays, which are really, just a high frequency, clumps of photon, and they're banging into the universe, the ether, right? They're flying into it. That means they're flying into the soup of force. Little force bits will hit them going this way and going this way and going different ways, and they're going to crash into more of that stuff going forward. And as they do, they start losing pieces of their gamma ray, and so they run out of gas, and that's the simple explanation. So the argument is, like, as I've stated it, I figured this out, a month ago? And so, yes, although I'd say there's conservation of energy in the sense that the bit of force always is going somewhere. It's always moving, all right? But the truth is, it can be in two states. It can be free, that is, traveling through space, like part of a photon or part of a magnetic field. It can be traveling through space, not pushing anything, or it can be pushing a proton and electron. And if it's pushing an electron, it's moving a little slower. And that's just the fact. So the fact is, it has more momentum when it's in free space. It's not being utilized, but it has it. And it has less momentum, in a sense, when it's pushing something, because now it's moving slower. So it gets from point A to point B a little slower when it's pushing something, which means that's a reduction in the overall momentum of the universe. So the universe loses a little bit of momentum by pushing electrons and protons around. So every time an electron or a proton moves, there's a little bit of a reduction in the total energy in the universe. Okay, now I'm not saying, obviously this piece of energy, when it's done pushing, it just goes back to going the speed of light. It's only reduced in its speed while it's pushing. So when it's going this way, it takes a little bit of energy out of the universe going that way, and then when it goes this way, it's going to take a little bit out of the universe going that way, and if it goes this way, it's going to take a little bit out of the universe going that way. And you can understand just how the jiggle of these elemental bits, that is, they're getting bounced around by this field that comes from all directions. So again, it's not that complicated, right? I mean, the pressure comes from the outside. If I put only one thing in the universe, this is how the universe will look. From that one thing's perspective, the universe is out to get it. A universe of chaos, a universe of stuff moving in all kinds of directions is going to look like it's all headed right for me. If I'm the only thing in the universe. And the idea is something, if there is a B out there, well, B is going to change the universe a little bit. And because of some of this energy being used up, the energy going this way, the speed of light, isn't going to get to it when it's supposed to. It's going to have reduced a little bit of its momentum by not traveling quite as far in the same amount of time. And that little reduction in momentum is going to be felt as gravity. So the simple explanation for gravity is that the elemental force in the universe, a little bit of its momentum is absorbed, pushing electrons and protons around. All right, so there's no contradiction in what I'm saying. I'm saying that this piece of energy still moves throughout the universe. It's still always going somewhere. It just goes a little bit slower when it's pushing an electron or a proton, and therefore the universe loses a little bit of energy. Again, it's not if I was to argue the ping pong paddle argument, let's just turn that thing off or something. What the hell? Stop it. Let's see if that helps. Alright, so what do I want to draw? See, those little distractions are just so irritating. Alright, so I wanted to make what point? Conservation. And the other conservation issue I could bring up. What the hell was it? Alright, so we have the idea that pushing the electron absorbs a little bit of energy, and then it goes back to its normal speed and goes about its business in the universe. So you're not destroying the energy, you're just slowing it down. Now, if I took the two ping pong paddle argument and I had one ping pong ball and I bounced it back and forth between those two paddles, you can understand that I would be increasing the energy by moving the paddles closer to each other. Now there's more impacts per second, okay? And each impact has the same velocity because you're not really changing the velocity of the ping pong ball. And so you could argue that there's more energy here. And so is that a violation of energy conservation to say, well, there's more interactions? There's not more energy in the universe. It's just that there's more or less interactions depending on proximity. So it's not an anti-conservational argument. It's just that you have to understand that energy manifests through these two principles. One, slowing the force down by having to push something, and another one by creating closer distances between pieces of reflective surface, which will cause more interactions. So the whole point is the thing that reduces the energy of the universe or increases it is the absence of interaction. The fewer interactions you have, the faster the force goes, but the less it's doing, and the more it's doing, the more interactions it's having, obviously it has to lose some momentum somewhere. So, whatever. You want to convolute and trick and play games with words and pretend there's a contradiction somewhere? Well, there isn't. Alright, so just be an asshole. I can't stop you. Owen. So then he says, then gravity would lose its energy over time, so your theory is not right. So that you think that simplistic pile of crap sentence is going to debunk something? So gravity would lose its energy over time. How exactly would it do that? I mean, the amount of energy it's losing is just the amount of distance. Like I said, one bit is moving, an electron, for example. And so it's a little bit of time momentum. That is, there's a point B, and it doesn't get to point B as fast, which means its momentum has changed. That's an obvious fact. And the change in that momentum, the change in the fact that, again, if I have an object that has a bunch of electrons and protons in it, and they're all moving in all kinds of directions, every little second they're moving in a different direction. They're just being jiggled about by the force. A little bit hits them from the bottom, then a piece hits them from the top, and then hits from the side, but it all balances out. It's pretty much even. And they're just jiggling about, okay? The fact is that that movement alone will account for a slight difference in the energy that goes in versus the energy that comes back out. The amount of energy coming back out will be a little bit less than the energy that went in because of the time, the speed difference. The force is a little slower when it has to move the matter, and therefore it has absorbed the energy necessary to create gravity. So I'm giving you a perfectly rational explanation for what causes gravity, completely consistent with mock gravity, which is the way they teach relativity, ironically. And this extension onto mock gravity, particle gravity, completely explains where the imbalance comes from, where the fact is why two bodies end up being attracted to each other is because they've created a deficit in the pressure between them. There's less pressure here than there is here and here. Because here and here the stuff is still moving the speed of light, and here it's been delayed, okay, by moving matter, so it's a less force, and the two bodies are pushed into each other. So it's a perfectly rational, physical, mechanical explanation for gravity, and perfectly consistent with every bit of real data we've ever observed. And yet you type this crud on my video. I mean, you know not what you do, you silly person. Just pathetic. So look, there's, obviously people don't want to pay any attention. They just do this crap on the internet where they type their little snarky bits. They don't pay any attention to the video they're watching. They don't watch whole videos. And then they certainly don't watch more than one video. And they think they're an expert and they just type crap. So really, unappreciated. Thank you very much. Try again. Grow the fuck up first. Try to do a little better than a fucking sentence. Let's see. Can you discuss your work on, so I guess this is another piece of satire or something, on the derivative. What's The derivative. What is that? The derivative. And non-Euclidean geometry. Why would I worry about non-Euclidean geometry? Why would I care about any kind of fake or phony geometry? I mean, we have a clear definition of dimensions. All right. I mean, I think it's a clear definition. All right. In the sense of the three dimensions, the key ingredient is they're all right angles to each other. I mean, I didn't draw these exactly perfectly, but you get the idea. They're all at right angles. So every dimension is a right angle to the other dimension. Now, there's no other way to put anything else in here, any other line that will obey that rule. So these three dimensions, okay, are solid. Now, why would I imagine something else exists? Why would I force there to be something else? Why would I say, well, the time does this, and the multiverse does that? Why would I bother with that crap? You have something really solid, three dimensions, and everything about everything we see in the universe indicates those are solid dimensions, that those are real things, that I can move away and towards you. I can move perpendicular to you, okay, and I can move perpendicular to you. Two of the dimensions are always perpendicular to each other, and the other dimension is always off the perpendicular. So two of them are always on the same flat plane, okay, no matter how you look at it. It could be these two on a flat plane, those two on a flat plane. That's another rule. Two of the dimensions have a twinness to them, and the other dimension is odd, No matter how you turn it around, you can make these two, and then, so I mean, this is solid. So you want to believe there's some other kind of geometry than those three dimensions. Why do you want to do that? I mean, why do you want to do that? Is that some sort of hairy anus thing or something? I mean, where does that come from? What's got you in the mood to talk about derivative and non-Euclidean geometry? Why should I waste my time with non-three-dimensional geometry? Won't be any answer. It's okay. Do you have videos on fluids? Thank you. Well, no, I really don't. Frankly, they're noisy. Okay, so studying fluids is, that's just doing a lot of generalizing. So you have to do a lot of integrals and mathematics because you really can't follow any bouncing ball. You have to just do it by some sort of group theory. And knock yourself out. But yeah, to me it's not elemental, of course. It's an emergent thing, fluids. Fluids is about what groups do. It's not about what individuals do. Okay. That does seem to solve the problem. So it's kind of a, this is on the strong nuclear force. So this is my argument that there's no strong nuclear force. That the irony is that what's holding the protons together is an electron. And it's provided by the neutron. So if you understand that a neutron is just an electron and a proton, then you can understand I could add another proton, okay, and I end up with an electron between the two protons. And then I can get protons very close because all the proton energy leaks out the electron, and all the electron energy leaks out the protons, and so I end up with no reflections in here at all. And therefore the external pressure is more than sufficient to push the two together, because I've created a low pressure. So it wasn't like I had to push things together with some sort of strong force. They gravitated together because I put something right in between them that lowered the pressure on both sides. And yeah, that solves the problem. We don't need any strong force. It does seem efficient than inventing a mysterious new force. One issue, though, while the neutron is found to have slightly more mass than the proton, well, again, how do you find its mass? This whole idea that we can, the mass of the proton is a little complicated, frankly. First off, it's charged, so how do you separate it from the the material universe and watch it fall in gravity, right? There's no, it's very hard to measure its mass in any kind of out of the context of its charge. So, hard to say. I find an 8.1% difference. Well, I don't know how, where did you find this? What experiment did you do to find this difference? So, in the mass between a neutron and a proton plus an electron. So, I don't know what that is. An 8.1 difference in the mass between a neutron and a proton plus an electron. So, I don't know where you get that difference from. I mean, I haven't seen that, so you're just saying it. So, what do I know about your 8% difference? As far as I know, there's no difference. I mean, the proton is a lot heavier than an electron. The electron's almost irrelevant. It's so tiny by comparison. I mean, 2,000 times lighter than the proton. So I don't know how you get an 8% difference, but whatever. I would argue that how you're measuring the proton is really measuring even the neutron. It's, you know, it's technically a dipole. And, you know, again, it's a little magnet maybe spinning. How do you measure the gravity of a magnet spinning? Like what piece of matter can you associate it with to measure it that isn't charged? You know, I mean, the only way we can measure things is to scoosh them up next to an atom and see what the atom does, right? I mean, it's not a whole lot of choices here. You know, but whatever. He has soy allergies apparently. Yeah, whatever. Alright, so that's all we got. It's depressing. Just no, you know, nothing, it's just nothing. So we'll do some more of this Wolfram guy. So this is much further on when he's babbling about modern physics. I'd like to, you know, this is some prodigy guy, you know. He was a physicist when he was, you know, he graduated from college, I guess when he was 21 or something. So, but anyway, you know, with a doctorate or something. I mean, you know what I mean. Much sooner than most. Anyway, you know, I wish he was rational. I mean, it's talking real physics, but it's just, you know, he's keeping all of the crap physics, all the crappy pieces, and then trying to computer model it as far as I can tell. But it all looks just, you know, it's squiggly lines all over the place. There's no rational geometry to anything he talks about in terms of his own theory. So in this part, he's just describing, you know, some of the history of physics, but it's the history of what they've said physics is. It's not really the history in terms of explaining how bad the evidence is for some of these conclusions. Like he mentions the Eddington experiment, and he says, oh, there could be something wrong with that experiment, but okay, it validated Einstein, you know, and so it's all this, you know, there's no real getting to the point that there isn't much evidence supporting this idea that there's anything called a dimension of time, or that space and time are somehow in some way woven into the same goo, and that you can bend the goo. Now, obviously, time is connected to distance, as I've just pointed out. So there's a clear relationship between time, like how long it takes a photon to get from point A to point B, and momentum. So that's the relationship, and I think that's what the evidence indicates. So anyway, we'll play some more of this crap.
One thing that was also
we need more volume-y
confusion that lasted a long time was the question of antimatter, and where was the antimatter in the universe? Because
yeah, well, why did you even invent it in the first place, and why do you think there is such a thing? And this all goes back to Dirac's equations, which were at the time he wrote them incomprehensible and useless, you know, because they assume things that are just silly, like electrons are in the same location and all kinds of wacky crap. And so what's the point? I mean, there's no reason to believe there's anything called an antimatter. I mean, there's just no good reason. There's no place for this stuff to function. It just can't do anything in the real universe. So I don't even know why they bother with this. And this whole idea that they're just using it as a placeholder. So this is where they're cheating time again. Because antimatter could be perceived as being every time they borrow from the future to justify an event. That is, they know the event will produce energy in the future. Okay, so the future will have more energy in it, in their equation. And what they do is they borrow it in the past in the equation and say, well, I just borrow the existence of that piece of energy because I know I'm going to give it back in the future. And, this is the convoluted kind of bullshit they pull. These are shenanigans, frankly. They're just mathematical shenanigans. It doesn't have anything to do with the real universe. There's no role for this antimatter to play. There's no place for it to exist. There's nothing it can do anywhere. It's just silly to think there's a place for it to exist. That there's a bunch of antimatter combining with my matter and destroying its existence and it's annihilating and all this. No, none of that crap is happening. And they fix it by saying, oh yeah, it annihilates, but then it just pops back into existence over here. So really all it is a way of teleporting matter from one place to another place and pretending that that's possible when that's not possible. It's just silly.
The most obvious theories of the Big Bang would produce equal amounts of matter and antimatter. It was discovered in 1964, a thing called CP violation, also related to time reversal violation. It's a phenomenon whereby there's sort of a difference between particles. Most things about particles and antiparticles are the same, but some particles and antiparticles have some strange small differences, particularly the neutral kaons, so the original example. But in any case, there was still this mystery. When I was a kid, still a big mystery. Why is there more matter? Why don't we see a bunch of, could there be antimatter galaxies? Could the Andromeda galaxy be made of antimatter? We didn't know.
I think we know. I think we know. So I'm just saying we know that everything sort of has to work on the same principle. That there can't be a bunch of atoms out there that have negative cores and positive on the outside, because they would interact in an insane way with regular matter. There wouldn't be any way for those things to be compatible.
My early science had to do with trying to figure out what the consequences of antimatter galaxies would be, and things about separation between matter and antimatter in the universe and so on. Actually, in the late 1970s, I worked on using CP violation to understand what I think is now the...
I mean, you have to have anti-light and anti-everything, then it's just silly. It's just silly. I just don't know why do they even indulge in this kind of conversation? Dark matter and antimatter. Why do they even play in this ball field at all? I mean, it's a beach ball in the middle of the baseball game, and you're just saying you're playing baseball. Why are you letting all of these erroneous balls into the game? I mean, it's just fucking everything up.
Accepted theory for why there isn't as much antimatter as matter in the universe, that there was CP violation in the early universe that caused a small difference between the amount of matter and antimatter, and all the stuff that wasn't different annihilated away, but we got left with a small residue, 1 part in 100 million, basically.
So all this annihilated away when there's just no evidence you can annihilate anything away ever, then anything ever annihilates. There's just nothing that gets annihilated. A little bit of a bit of the force can be absorbed in the sense of it can slow something down, but there's no evidence you can ever annihilate electrons and protons. I mean, it's just, why are they even having this conversation?
That is everything we know. That's the matter in the universe. So that's one kind of weird feature. By the way, the one thing about antimatter is antimatter still falls, doesn't have negative mass, still has positive mass. I now understand.
Yeah. Well, because you say so. Again, not because you have any experiment to prove so. So again, it's just silly. Right. So why is that? Oh yeah, antimatter has regular mass. Well, why? Because it's just reversal, right? It's just protons where the electrons should be, which is retarded.
Why that's true. But that was originally kind of just a fact from quantum mechanics. In any case, back to general relativity. So what happened in general relativity was sort of progressive measurements. Things got more accurate. A lot of very nice experiments done on the effect of gravitational redshift, all kinds of other things, predictions done.
So again, not a great deal of experiments and tiny pieces of evidence, and the evidence can be interpreted in lots of different ways. Clearly, lots of the experiments can be understood as scatter. clearly even the redshift arguments can be, the argument can be made that the redshift is a consequence of the fact that there is no perfect vacuum anywhere, and that light's always going to get degraded with distance, just through natural scatter with occasional atoms. I won't say scatter, let's say transmission through transparent atoms.
So the binary pulsars, neutron stars orbiting each other, emitting gravitational waves, just like you can emit electron.
So it's just like you can emit electromagnetic waves. So let's understand, it's nothing like electromagnetic waves. It's nothing like the simple argument I've made, where if I move towards you, more light reflects, I get brighter. I move away from you, less light reflects, I get invisible. So if I go fast enough, I'm invisible. Just a fact. It's a deducible conclusion. Okay, you can figure that out. Okay, that light has a certain speed. If I move that speed, the light can never get to me. That means it can never reflect off me. Therefore, you're not going to see me. If I'm not emitting light, then how are you going to see me? You're not going to be able to see me because I'm not going to reflect anything. So gravitation, so electromagnetic, the argument I would make to you is that it's always antenna based, and even when the antenna is just a number of atoms inside of a substance with the very small photon types, okay, it's still an antenna. So the big wavelengths have a big antenna, the little wavelengths have a little antenna, okay, inside the molecular crystals that actually produce light. Most of the stuff that produces light by shooting a bit of electricity into it, okay, are metals, because they have crystals, and the crystals are producing the photons, and they're doing it by moving. All right, and the simple truth is that if I take some electrons and I move them away, then I'm not going to be, the universe, the force will be chasing it, right? And if it's moving half the speed of the force, then half of this force is going to reflect off of it, and it's also changing its position. So it's not only moving, but it's changing its position as it's moving, which means it's getting further away. Okay, so less of this force is going to reflect. You can sort of understand that, right? The force can't catch up to it. It's not going to hit it where it was. It's going to hit it in some other location. So therefore, it's going to come back later than it would have if it just stayed where it was. So it's going to reflect less. And then if it's moving towards, then it's going to reflect more. So you could just understand, if I wobbled an antenna back and forth, and let's say I could wobble it very fast, you can understand that when it's wobbling this way, okay, then this side of the universe looking at it, okay, sees it disappear. It's not seeing anything. It's seeing a zero. Right? And then when it wobbles this way, it's seeing twice as much. Right? So now it's seeing a lot, And then it sees nothing again, and then it sees something again, and that's called a frequency. Okay? That's a frequency. You have stuff, you have nothing. You have stuff, you have nothing. You have stuff, you have nothing. That's a frequency. And so that's what you're seeing. You're seeing this antenna's moving. The world, as it reflects off of it, is changing. So when it's moving away, it's not reflecting anything. When it's moving towards, it's reflecting twice as much. And that's all that really is making electromagnetic waves. So if you understand gravitational waves, they made up a whole theory for those. Now, if it was a simple thing of just saying, okay, here you have two bodies orbiting each other, okay, a binary system. That's what most of these all of the gravitational waves are based on, is some binary system where the two objects are caught in some gravitational thing and they're spinning around each other. And the argument would be, at any one moment, this one's moving away and this one's moving towards. Well, that doesn't help you very much, because that's one saying on and one saying off. And from your perspective, you're not going to be able to see the difference. So you're just going to see one. You're going to see on and off. So you're going to see in between on and off. You're going to see something in between something and nothing. So that doesn't really explain it. Now, the tiny bit of gravity change when they're lined up this way versus when they're lined up this way. So you could say from an observer's point of view, there's a tiny bit of gravity change. So when they're lined up this way, the gravity spread over a larger area. All right, so the point source is bigger, and so the gravity's weaker. And when they're lined up this way, it'd be a little tiny bit stronger because the gravity's lined up, and it's a smaller point source. So, but that's all you have. All right, now gravitational waves isn't made out of that. So it's not made out of this idea that the center of this, see this two-body thing, if I have two things orbiting each other, the argument is that the center of gravity changes a little bit when they're in this position versus this position. And so it just moves a tiny bit forward. Right? So all you really have is this change. The center of gravity moves a little bit like this. So you could argue that that produces a signal. Now it's so tiny and they're so far away that there's no hope, and Einstein said that. So again, it brings up Einstein, and it's not Einstein that wouldn't like this gravitational wave crap at all. And he never theorized about what they're saying. So what they're saying, because that signal's way too small, this little tiny jiggle in the center of gravity of the two-body system is so slight that there's just no chance it would get here. So what they had to do was create some scenario where as these two things are circling each other, they're ripping matter off of each other. And they're ripping it off in a sense where it's not energy. Like they're not ripping off electrons and protons and photons. They're not creating regular radiation. They're actually creating bent space, whatever that is. Okay, so it's not any kind of gamma, beta, or alpha. No, it's some sort of new form of energy, so that whole solar masses are in an instant of time, okay, stripped off of this object, and this object, and that this new bent space, stuff is created. And so every time they go around, they're stripping this stuff off. And even that, though, doesn't make any sense because they're stripping it off constantly. So where do you get the wave from? So you still don't have a wave anywhere. Unless you make this spiral go smaller and smaller or some kind of other thing. I don't even know how that would help you that much. But anyway, that's what they're turned it into. So they're stripping matter. They're converting matter into bent space to create enough energy for it to get here. And they create it in a form where, see, if they created regular energy like gamma rays and beta and alpha, then the rest of the universe, all the stuff around this thing, would get blown away by a tremendous amount of energy. An insane amount of energy being released in 1 second. Okay, this thing is releasing just like I said, it's an insane amount of all the light in the universe right now. Okay, that's what it equals. Okay, so if it took all the light in the universe for the next 4 seconds, that's how much energy this one thing is releasing. And it's like bullshit. Okay, because it doesn't do any damage to anything, and somehow this wave goes all the way, billions of light years through space, and it gets to the Earth, and it moves a mirror, 1/4 of a proton's hair, and somehow we measure that. It's preposterous theory. It's nonsense. It's garbage. And everybody falls for it, and everybody just, we did it, says you. The evidence sucks. It's so weak. It's so, that's an extraordinary claim, and they don't have even ordinary evidence. And then when you look how complex they've made their interferometer, how many wacky bits are in it now. They got 36 layer mirrors. How do 36 layers of mirror make your mirror more reliable in terms of how deep the photon goes into it before it's reflected? How does 36 layers help do that? Making your mirror thicker, how does that make it reflect the photon sooner, more reliably at the same distance? It doesn't make any sense at all.
waves when you have moving electric charges, so you can emit gravitational.
So again, so we know that moving charges, that means just moving electrons and protons, and that just means in the antenna you're moving them. And again, if just think of it moving towards and away from you. That's all you're doing. You're moving them towards and away, towards and away, towards and away. And when you're doing that, you're, changing what you're seeing.
When you have moving masses, that was a prediction of Einstein's general relativity, so that was there was indirect observation of gravitational waves through these binary pulsars, things like that.
There wasn't any indirect gravitational wave observation, no. And again, they never even tested their interferometer. They could just swing a lead ball over the mirror, outside the tunnel, just swing it back and forth and see if their mirror can see that. Because if their mirror can't see that, it can't see anything 5 billion light years away.
Relativity was working great. Theory from 1915.
So again, it just keeps saying it. It's all this hype about all this, they have all this great evidence and all this great mathematics, and it's just hype. They just say it, okay? And when you poke at it a little bit, like the two-slit experiment, you just poke at it a little bit, scratch, 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 and it all falls apart. The coherency of their mathematics, all their big, bold statements about how all perfectly it fits and all this crap, and you find out they're not even using the right pattern. They're not even describing it. They're not even drawing the right pattern. I mean, it's clearly, I did look in Feynman's book of his lectures, and the drawings are the young two-slit experiment drawings, two waves going out with the centers in the middle of the slits. That's not even their own mathematics. So it's just so bad and so corrupt.
No changes, working great. And in fact, to this day, it's worked great. And the big
see, again, it just says it. It works great. Great for what? Where does it work great? Where? Where's it done?
Thing in when was it? 2015. Discovery of gravitational waves by LIGO was the merger of two black holes causing a very violent thing where about 2 times the mass of the sun is dissipated in energy in a matter of a second.
So he said dissipated as energy. It's not the truth. It's not any form of energy anybody knows of. It's not heat. It's not light. It's not Hawking radiation. It's not any kind of radiation ever known to mankind. So again, that's just saying crap, because that's just crap. It's not in any kind of force or matter form. It's not in the form of any known force or any known matter.
About a third of the way across the universe. And that produced this intense pulse of gravitational waves that was detected by gravitational waves deform space-time. And so what?
Yeah, deformed space-time. That's what it is. It's deformed space-time. So it turned matter into deformed space-time. A theory Einstein never proposed. So Kip Thorne makes up this notion that somehow he can convert matter into bent space. He can bend space by destroying matter. There's no evidence that anybody can do that, or it's ever been done, or anybody else proposed it except him. And everybody else is just saying, sure, why not?
What LIGO does is it basically is looking at the length of a big thing, and it's basically saying if there's a deformation in space-time, like a wave comes through space-time, the length will change just a little tiny bit, a tiny fraction of the distance across an atom. The length.
Yeah, tiny distance. They're saying of a proton. They're saying they're measuring thousands of times smaller than the width of a proton in length in change. In a beam, they've bounced 1,600 times off mirrors, and they're measuring differences in the beams that are just that tiny. They can't even be reliably bouncing off atoms. They don't know how many atoms deep the photon goes before it bounces back. How can they sit there and make these claims? They're ludicrous claims.
Will change to represent the passage of the gravitational wave, more or less. And that was observed in 2015, a fantastic validation of general relativity and of the existence of black holes.
So again, it has nothing to do with general relativity, and it certainly doesn't have anything to do with Einstein. Einstein wouldn't be very pleased at all that you put all these words in his mouth. He overtly stated he didn't have any belief in there would be any detectable gravitational waves. He stated it overtly, and yet they just sit there and say, well, Einstein didn't mean that. Yeah, I think he did mean it.
Okay, so the one thing that, it's like the one kind of big flag that something doesn't really quite work in physics is the fact that this whole structure of quantum field theory is completely inconsistent with the theory of gravity. So the problem is you try and make a quantum theory of gravity. The most obvious way to do it is replace photons by gravitons, and
So again, gravitons in what form? Their graviton would again be a force carrier. It would be some Volkswagen that sends a message to something, and then the passenger gets out of the Volkswagen, the Volkswagen goes elsewhere, and the messenger's got a sign that says stop or go. It doesn't make any sense. I mean, if you're going to create a graviton, you create it as something moving in from the outside, pressure from the outside, not some force carrier, that comes from the inside and flies out to something and tells it, come towards me. It crashes into it, and somehow crashing into it makes it move towards me. I mean, it doesn't make any sense.
stir the pot, so to speak. Well, if you do that, you get a theory that isn't renormalizable and it's a big mess. So people starting in the 1980s really got excited about doing quantum gravity, finding a way to merge kind of quantum field theory and gravity. And there were these different schemes, things like supergravity, schemes that said, let's add more particles. Well, those particles weren't observed. Other kinds of...
That's right. So they're all schemes, and yeah, I would argue that could call any of these ideas a scheme. And the problem is theirs don't solve the problems with something simpler. They keep trying to make... keep trying to keep all of these extra superfluous balls they've created in the game. So they keep saying, well, let's redefine the rules of baseball. And they keep trying to do it in the context of, well, yeah, beach balls are allowed and cannonballs are allowed. And, they have all these extra balls in the game. And they're never going to make baseball out of it, as long as they keep trying to put all these wrong balls in the game.
For merging gravity and quantum mechanics. Another thing that emerged was a retooling of string theory. String theory was originally invented as ultimately unsuccessful theory of strong interactions, but it was sort of retooled and put to work as a theory that would unify quantum field.
And it's just the silly notion that, well, we can't explain the push-pull, so we're just going to make springs eternal and elemental. So all string theory really was saying was, we're going to make the spring, the compress and decompress, we're going to make the jellyfish elemental. So now we have little elemental jellyfish. So it's really just a jellyfish theory. I mean, it really is. They can't explain why there's push and this illusion of pull. And so they have to make something elemental that's doing this crap. Because they haven't figured out that pull is just the absence of push.
In gravity, a sort of a consistency condition of string theory is general relativity, et cetera, et cetera, et cetera. It had some weird predictions, like the universe is really 26-dimensional, but most of those dimensions are rolled up in little tiny balls and so on. Kind of weird things that to many people might be kind of a sign there might be something unconvincing about this theory.
Yeah, to many people. Not nearly enough people, apparently. But yes, you're just so depressing. I mean, all this, the fact that you'd even go near any of this horse shit. Oh, we're going to make extra dimensions to hide all of the stuff that doesn't make any sense. I mean, it's just so obvious that you're just sweeping it under the rug. We can't deal with it. Dark matter. Yay, it fixes it. Imaginary God of the Gaps answers. I mean, this is so these are all atheists who would sit there and talk about how bad and stupid religious people are, and how could they deny evolution. Evolution has so much evidence, and here they are proposing nonsense answers. They're just as bad as God. They're just as bad as the silly answer that God was.
But people didn't have much choice, so physics community kind of barreled right along, and a lot of physicists started working on string theory.
You had plenty of choice. You could choose to get on the motorcycle and jump the shark, or you could sit there and be dignified scientists and say, yep, we haven't got enough info. Haven't got it right yet. But instead you just had to sit there and say, no, we're great, we're super, we've done it. We did it.
And there were some excitements in the mid-1990s. There was a thing called M theory, which had sort of emerged from some sophisticated string theory. For whatever it's done in physics and whatever it will do in physics, it has spun off a lot of very nice mathematics.
Whatever. So they always claim that there's this very nice mathematics that it's just infinity divided by double infinity. It's bullshit mathematics.
merger of mathematics with physics that has been associated with it is really very powerful. And I might say that in the physics that I've been doing recently, I think that string theory, its mathematics is quite relevant, although its underlying structure is not the same. But string theory has been sort of recast once before. I think it can happen again and still leave the same string theory structure.
Right. So there's nothing, again, like I say, I've looked up his counter theory and it's wooier than their theory. It's just there isn't a straight line anywhere in it. Might as well be just Ken Wheeler hyperburloid fun.
Intact, so to speak. But the thing that happened so quantum gravity, big thing in the 1980s, 1990s, and so on. One piece of that had been 1974. Stephen Hawking worked out this idea of Hawking radiation, which was sort of a rather rickety kind of calculation of sort of a merger of quantum field theory.
So at least an admission that it's rickety. This is marginal. Deriving shouldn't be contriving. Yeah, and it looks a little bit contrived, doesn't it?
What happens to quantum field theory near a black hole? And the basic answer is you can have situations where virtual particle pairs are made,
Yeah, so here we go, virtual particle pairs. So there's just no evidence that anything's paired with anything else. The only pairing there is when you wobble the antenna this way, one side sees one thing, one side sees the other, and then when you wobble it back this way, they do exactly the opposite. So obviously if I'm creating on this way, I'm always creating Mr. Off over here. And when I'm creating off over here, I'm creating Mr. On over there, that kind of thing. So there's pairs in the sense that things are correlated. So you could have two photons leaving that are exactly inverse. This one's XO, 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 and this one's OX, OX, OX. But there's no other notion of relationship except right-hand glove, left-hand glove.
The pairs are made, one of the pair falls into the black hole and the other one is emitted to infinity, and that leads to a black hole not really being black, but emitting radiation. Hawking radiation hasn't been observed yet, but it's a great theoretical interest, and actually I think we have some very interesting new things to say about it.
I don't think so.
But in any case, that led to a bunch of kind of theories around kind of thinking of black holes. So black holes, even though they're big, kilometers across and so on, whatever it is, or even bigger than that, they are in a sense very perfect. There's, if you have a black hole.
So the only argument to that is all he's really saying is the force of symmetry is very strict. You can't have a mountain on a black hole. It won't tolerate mountains. Okay, you can't have any blemishes, any bumps, bimps. No bimps allowed on black holes. So they end up creating perfect spheres.
It doesn't have any hair. There's a no hair theorem for black holes actually, but it's basically like all you have to know about a black hole is its mass, how fast it's spinning, and maybe its electric charge, and everything else.
It's kind of a silly word to use, right? It's electric charge. I mean, come on. This is the electric universe wacky crap. There's no charge on a frickin' black hole.
Like a particle, really, but it's just a great big particle. And so that idea of a black hole is just like a particle is something that has sort of wound its way into theories of sort of attempting to merge quantum mechanics and gravity, particularly from the late 1990s, I think, with the ADS-CFT correspondence. It's a correspondence between anti-de Sitter space, which is...
So again, I'll just reassert, there's only one universe, and it's the little tiny one. The electrons and protons are in the only universe. They're the things being bounced around in the real universe. And everything else is a bizarre, emergent property kind of thing. Just as we are not really living things. We're not cells. We're made of cells. So, and the cells are what make you function. Without the cells doing what they're doing, you don't do anything. They do it first. Your neurons fire. You don't fire your neurons. The small universe makes the big universe. It's not the other way around.
A version of the solution to Einstein's equations, and a thing called conformal field theory, which is kind of a limiting case of quantum field theory. And there's a very beautiful mathematical correspondence between these.
Again, more beautiful mathematics, blah, 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 blah. I mean, they won't be able to show you that in any form at all. They won't be able to show you anything beautiful, ever, in their mathematics.
Which I think actually is a precursor of something that we now understand much better, but that has to do with the merger of relativity and quantum mechanics. But anyway, I think we're pretty much, well, that's kind of well, I've been talking there about fundamental physics. There are two big branches I haven't talked about. Maybe another time I'll talk about these. One is condensed matter physics, things like theory of superconductivity and so on. That was a field that really started.
Well, there's only one kind of physics. It's physics. Okay, so there's just no point in all these specialties, but whatever. Okay, so we've done the bit here. I wish I could find some more. I mean, like he did another one of these, but I haven't found any other one that talks about anything reasonable. So anyway, so whatever. Blah blah blah. Just more stuff to put in the pile of stuff and to consider and whatnot and so forth and blah blah blah. So disappointing. Blah 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 blah. Blah blah. So till the next time and such, and no. Endeavor to persevere. Blah 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 blah. Blah blah blah.